All right, so 9.3. If we're talking about 9.3, a lot of this, I'm going to say like this stuff here, where the book suggests, I'd recommend instead just use your graphing calculator, put the equation in, then please don't copy the graph off the graph screen. Do the table so you can actually get the right dots on the graph and then do your smooth curve through it. But for the Y-intercept, if we have a parabola, we're talking where that thing hits the y-axis. Agreed? That spot right there? So do we know the x value or the y value every time? That's maybe a bad question. Do you agree the x value has to be the number? Zero. So that's kind of what I was looking at. But the y-intercept is going to be what's the y value for the quadratic, the graph, the parabola, when x is 0. Where does it touch the y-axis? Good? And then this line here is what I kind of got excited about, started talking about. I'd recommend, so if you have that app that I like or a graphing calculator, just plug in the equation, use the data table, put the points on, do your curve. Good? And that's what I would expect you'd probably do on like a quiz or something along those lines. The book suggests they go through and say, well, if you have the equation, like, maybe I should say this. If the y-intercept is where x is 0, do you agree if I put a 0 in for both of these, this part here just becomes 0, right? 4 times 0 is 0. Mm-hmm. And 0 squared times anything is just 0. So when we're talking about that y-intercept, the only thing that's left every time is the c value, if it's ax squared plus bx plus c. So if you're trying to graph something, you should be able to, if it's in this form, real easily get your y-intercept and just know that that's going to be something like that there, the 1. Fair enough? Actually, that's probably not a good spot for the 1. But okay, so we'll be able to know what the point is. Good? All right, so we have this equation here. And I went through and found, okay, what's the y-intercept? Then I put in some numbers for x, found some y values. Let's graph this thing, shall we? So instead of doing the data table, I just gave you some points. So our y value needs to go up to at least this 17. So up here I'm going to say 20. And 10 would be halfway up. And you could put in 5 and 15 if you wanted to between those. And I'm just going to go from -2 up to 2. And now for our points, this 0, 1. Do you agree that's going to be right about there, 1/5 of the way up to 5? So, something like that. So we have a dot there. And then when I go 1 to the left, then I go down. That can't be right. Because if I have this 1, 7, I have papers blowing in the wind. So if I have this 1, 7, agree the 1 is going to be over here? The 7 is going to be right about there. So 1, 7, maybe we'll say that's this one. I'm going to be right about here. Is it possible that I'd have -1, -1? Because our parabolas are supposed to be symmetrical, agreed? It's supposed to do something like this here. I'm a little low on that side. But it should be -1, -7. I'm sorry, -1, +7. So this one should be -1, +7. Where that probably came from is when we take and type into a calculator, like, let me back up. If I write 2 times -1 squared, in a lot of the graphing calculators, that's going to give the wrong answer. When it sees this -1 squared, it's going to say the answer to that is a -1, and 2 times -1 is a -2. But instead, -1 squared is +1, and 2 times +1 gives you a +2, agreed? So you have to be a little careful if you're going to take and punch them into the equations, that if you have something like that, if you have a negative to an even power, you either need to put it in parentheses or just treat it like a +1, just type it as a +1. We okay on that? All right, so we fixed that point, so scribble that baby out. All right, 217 over 2 up 17, right around there-ish. So I can kind of get in that side. And where is it going to be over here at -2? Yep, -2, 17 also. And so if I try to do that side, see how well I can make my curve. So something like that. Wow, I'd like to think my graphs usually look better than that. Oops. But we good enough? I guess I can't get rid of that. So. All right, then. Try to make yours prettier than that. Solving story problems. So if we have story problems, a lot of times these are going to be a ball's thrown up in the air, or a ball is dropped, or something like that. The initial height, if we're looking at a graph, make this a little bit bigger. So if we're looking at a graph for a thrown object, maybe we should make it something like this here. If we were, I don't know if I draw it or not, but if you have something like that, it's going to be a curve, maybe something like that. So some dude's on a building, he throws a ball kind of up off a building or a water balloon. He's in college, he's trying to bomb some girls that are laying out in the spring weather. And so he's up on the sun deck, chucks a water balloon up. Okay, so anyway, so starts at this initial height. Do you agree this is where it starts? Maybe it's 30 feet up? And purely hypothetical situation, of course. But so no experience with that. Actually, I never did throw water balloons at girls sunbathing. But okay. These notes are going nowhere fast. They're nowhere good. Okay. Initial height, the starting height's always going to be the Y-intercept, right? Because that Y-intercept is what is it going to be when x is 0, and time is pretty much always on the x-axis. Fair? So we have that. The highest or the lowest time. Do you agree the ball is going to be the highest, or the water balloon is going to be the highest right there? What's that point called in our... That's called our vertex. So now, is it going to be the x value or the y value of that vertex? The x, nice. So it's going to be the x of the vertex. And if we have the equation for the quadratic or for the vertex, anyone remember how you find that x value of the vertex? Same as the axis of symmetry? X equals? Nice. Nice. Negative b over 2a. So take your equation, find the b, what's in front of the x to the first, find the a, what's in front of the x squared, pop it in, you're good. Okay. So the highest, lowest height value, so this here is kind of like the time. The y is like the height, because this would be like the height over on the y-axis. So this here is going to be the y of the vertex. Agreed? Because the y is going to be the height for a graph like that. And when it hits the ground, well, it hits the ground over here. That's going to be our X-intercept. Now, if we're looking at a parabola, we're going to go over different ways to find X-intercepts. But you agree the rest of this parabola would come down something like this within the limits of my drawing ability? So do you agree you have a second X-intercept right here? Does that mean anything for this story problem? No, because that would be like, what time would it be leaving the ground, to get at the person's hand up here when he launches it? So it's kind of before the water balloon is thrown, so it doesn't matter. It's just kind of an extraneous and extra solution. Fair enough? Cool. Then let's move up here. Height of a soccer ball. So we're kicking a soccer ball. Here's our equation for it, right there. The initial height of the soccer ball is... said the initial height is c. What's the c value in this equation?
0.
Nice, because it's ax squared plus bx plus c. Yep, so it's kind of like we have this 0. So this here is going to be initial soccer ball with a height of 0. Good? And then, if we look at this later, you're going to get one of two numbers in here, and I may be getting a little ahead of myself, but if you have a negative 16, it's going to be measured in feet. If you have a 9.8, so if a equals negative 4.9, then it's going to be in meters. So because they have this negative 16, we know that we're measuring in feet off the ground. So the height's 0 feet. Fair enough? So we have right now a situation where somebody's ball is on the ground at 0. And we're going to take and kick this thing, and it should hopefully look kind of symmetrical, something like that. Good? So what's the ball's maximum height right there? That's our vertex. So to find it, we're looking for this number right here. Agreed? The height or the y value. We can't find the y value right away. First we need to find the x value. And x equals negative b over 2a. That'll tell us the x value, or what's this axis of symmetry there. So I have negative 32 over, 2 times negative 16, which is another negative 32. So in other words, we get a 1, right? So at 1 second, this baby reaches its highest point. So now to find the y value, we could take and put a 1 in for both. So I'm going to recopy the question a second. So here's our equation, plus 32x. So if I take and put a 1 in there, so negative 16 times 1 squared plus 32 times 1. So we find the height is 16, I believe. Right? And it'd be 16 meters, 16 feet. Feet, yep, because that first thing was the negative 16. So our ball gets up to 16 feet in the air. When does it reach its maximum height? Nice, so 1 second. When does the ball land? When it hits the ground. Why can you say 2 seconds?
Because it's 1 second to get in the maximum and then 1 more to get down.
Yep. Now that won't work. That won't work for a problem like this. So if you know the vertex is here, do you agree that's halfway to this height again? So you can't do it all the time. If it has a C value, if it starts off the ground, that won't work. But if you have one like this where it starts on the ground, goes up, comes back down, if this is 1 second right here, then you know this is going to be 2 seconds because it's symmetrical. The vertex will be halfway across. So when does the ball land? 2 seconds. And that's it for the section.
Yay.